All right, welcome back to another video. So I could work on the hugging face more. That would be good. I'm afraid I'll get behind on that. But I just want to read more of this book. This is a really good book. And I'm finally past kind of some of the less practical stuff. So chapter 5 is all about prompt engineering, which is going to be really important to know now, as well as in the future. So, I just want to hear what the author has to say about prompt engineering and keep this book going because this has been a really good book so far. So, with no further ado, I'm going to start chapter 5, prompt engineering. Prompt engineering refers to the process of crafting an instruction that gets a model to generate the desired outcome. Prompt engineering is the easiest and most common model adaptation technique. Like fine-tuning, prompt engineering guides a model's behavior without changing the model's weights. Thanks to the strong base capabilities of foundation models, many people have successfully adapted them for applications using prompt engineering alone. You should make the most out of prompt engineering before moving to more resource intensive techniques like fine tuning. Prompt engineering's ease of use can mislead people into thinking that there's not much to it. At first glance, prompt engineering looks like it's just fiddling with words until something works. While prompt engineering indeed involves a lot of fiddling, it also involves many interesting challenges and ingenious solutions. You can think of prompt engineering as human to AI communication. You communicate with AI models to get them to do what you want. Anyone can communicate, but not everyone can communicate effectively. Similarly, it's easy to write prompts, but not easy to construct effective prompts. Some people argue that prompt engineering lacks the rigor to qualify as an engineering discipline. However, this doesn't have to be the case. Prompt experiments should be conducted with the same rigor as any ML experiment, with systematic experimentation and evaluation. The importance of prompt engineering is perfectly summarized by a research manager at OpenAI that I interviewed. The problem is not with prompt engineering, it's a real and useful skill to have. The problem is when prompt engineering is the only thing people know. To build production-ready AI applications, you need more than just prompt engineering. You need statistics engineering and classic ML knowledge to do experiment tracking, evaluation, and dataset curation. This chapter covers both how to write effective prompts and how to defend your applications against prompt attacks. Before diving into all the fun applications you can build with prompts, let's first start with the fundamentals, including what exactly a prompt is and prompt engineering best practices. Introduction to prompt engineering. A prompt is an instruction given to a model to perform a task. The task can be as simple as answering a question, such as who invented the number zero. It can be more complex, such as asking the model to research competitors for your product idea, build a website from scratch, or analyze your data. A prompt generally consists of one or more of the following parts. Task description, what you want the model to do, including the role you want the model to play and the output format. Examples of how to do this task. For example, if you want the model to detect toxicity in text, you might provide a few examples of what toxicity and non-toxicity look like. The task. The concrete task you want the model to do, such as the question to answer or the book to summarize. Figure 5-1 shows a very simple prompt that one might use for NER, named entity recognition task. So figure 5-1 is simple prompt for NER. So task description, given a text, extract all entities. Output only the list of extracted entities, separated by commas and nothing else. So, for example, text Brave New World is a dystopian novel written by Aldous Huxley, first published in 1932. So, entities Brave New World, Aldous Huxley. So, the task would be text, the text you want to extract entities from, and then entities. For prompting to work, a model has to be able to follow instructions. If a model is bad at it, it doesn't matter how good your prompt is, the model won't be able to follow it. How you evaluate a model's instruction following capability is discussed in Chapter 4. And let me do a quick break. I'll be right back. All right, I'm back. So continuing on, how much prompt engineering is needed depends on how robust the model is to prompt perturbation. If the prompt changes slightly, such as writing the number 5 instead of FIVE, adding a new line or capitalizing or changing capitalization, would the model's response be dramatically different? The less robust the model is, the more fiddling is required. You can measure a model's robustness by randomly perturbing the prompts to see how the output changes. Just like instruction following capability, a model's robustness is strongly correlated with its overall capability. As models become stronger, they also become more robust. This makes sense because an intelligent model should understand that the digit 5 and FIVE mean the same thing. For this reason, working with stronger models can often save you headaches and reduce time wasted on fiddling. Tip: experiment with different prompt structures to find out which works best for you. Most models, including GPT-4, empirically perform better when the task description is at the beginning of the prompt. However, some models, including Llama 3, seem to perform better when the task description is at the end of the prompt. In context learning, zero shot and few shot. Teaching models what to do via prompts is also known as in-context learning. This term was introduced by Brown et al. Of 2020 in their GPT-3 paper, Language Models Are Few-Shot Learners. Traditionally, a model learns the desirable behavior during training, including pre-training, post-training, and fine-tuning, which involves updating model weights. The GPT-3 paper demonstrated that language models can learn the desirable behavior from examples in the prompt, even if this desirable behavior is different from what the model was originally trained to do. No weight updating is needed. Concretely, GPT-3 was trained for next token prediction, but the paper showed that GPT-3 could learn from the context to do translation, reading comprehension, simple math, and even answer SAT questions. In-context learning allows a model to incorporate new information continually to make decisions, preventing it from becoming outdated. Imagine a model that was trained on the old JavaScript documentation. To use this model to answer questions about the new JavaScript version without in-context learning, you'd have to retrain this model. With in-context learning, you can include the new JavaScript changes in the model's context, allowing the model to respond to queries beyond its cutoff date. This makes in-context uh, learning a form of continual learning. Each example provided in the prompt is called a shot. Teaching a model to learn from examples in the prompt is also called few-shot learning. With 5 examples, it's 5-shot learning. When no example is provided, it's 0-shot learning. Exactly how many examples are needed depends on the model and the application. You'll need to experiment to determine the optimal number of examples for your applications. In general, the more examples you show a model, the better it can learn. The number of examples is limited by the model's maximum context length. The more examples there are, the longer your prompt will be, increasing the inference cost. For GPT-3, few-shot learning showed significant improvement compared to zero-shot learning. However, for the use cases in Microsoft's 2023 analysis, few-shot learning led to only limited improvement compared to zero-shot learning on GPT-4 and a few other models. This result suggests that as models become more powerful, they become better at understanding and following instructions, which leads to better performance with fewer examples. However, the study might have underestimated the impact of few shot examples on domain specific use cases. For example, if a model doesn't see many examples of the IBIS data frame API in its training data, including IBIS examples in the prompt, can still make a big difference. Terminology ambiguity, prompt versus context. Sometimes prompt and context are used interchangeably. In the ChatGPT, in the GPT-3 paper, which isn't ChatGPT, Brown et al. 2020, the term context was used to refer to the entire output into a model. In this sense, context is actually the same as prompt. However, in a long discussion on my Discord, some people argued that context is part of the prompt. Context refers to the information that a model needs to asks it perform what the prompt asks it to do. In this sense, context is the contextual information. And I think I might have tried to join her Discord before. Oh, wait, what? I'm confused. Uh, oh, oh, okay, there we go. All right, so now I'm a part of the author's community. Oh, a few steps. So, okay. All right. All right. Moving on. To make it more confusing, Google's Palm 2 documentation defines context as the description that shapes how the model responds throughout the conversation. For example, you can use context to specify words the model can or cannot use, topics to focus on or avoid, or the response format or style. This makes context the same as the task description. In this book, I'll use prompt to refer to the whole input into the model, and context to refer to the information provided to the model so that it can perform a given task. Today, in-context learning is taken for granted. A foundation model learns from a massive amount of data and should be able to do a lot of things. However, before GPT-3, ML models could do only what they were trained to do, so in-context learning felt like magic. Many smart people pondered at length why and how in-context learning works. See, How Does In-Context Learning Work by the Stanford AI Lab. Francois Cholet, the creator of the ML framework Keras, compared a foundation model to a library of many different programs. For example, it might contain one program that can write haikus and another that can write limericks. Each program can be activated by certain prompts. In this view, prompt engineering is about finding the right prompt that you can activate that can activate the program you want. System prompt and user prompt. Many model APIs give you the option to split a prompt into a system prompt and a user prompt. You can think of the system prompt as the task description and the user prompt as the task. Let's go through an example to see what this looks like. Imagine you want to build a chatbot that helps buyers understand property disclosures. A user can upload a disclosure and ask questions such as, how old is the roof? Or what is unusual about this property? You want this chatbot to act like a real estate agent. You can put this role-playing instruction in the system prompt, while the user question and the uploaded disclosure can be in the user prompt. So here's the system prompt. You're an experienced real estate agent. Your job is to read each disclosure carefully. Oh, and I need to disable. Oh, I need to. Oh, hold on a second. All right, I'm back. Let's keep going here. So I got distracted a little bit. So here's the system prompt. So you're an experienced real estate agent. Your job is to read each disclosure carefully, fairly assess the condition of the property based on this disclosure, and help your buyer understand the risks and opportunities of each property. For each question, answer succinctly and professionally. User prompt context disclosure.pf. Question. Summarize the noise complaints, if any, about this property. Answer. Almost all generative AI applications, including ChatGPT, have system prompts. Typically, the instructions provided by application developers are put into the system prompt, while the instructions provided by users are put into the user prompt. But you can also be creative and move instructions around, such as putting everything into the system prompt or user prompt. You can experiment with different ways to structure your prompts to see which one works best. Given a system prompt and a user prompt, the model combines them into a single prompt, typically following a template. As an example, here's a template for the Llama 2 chat model. So there we go. Um, okay. User message. Okay, so these are extra characters, special characters, it looks like. If the system prompt is translate the text below into French, and the user prompt is how are you, the final prompt input into Llama 2 should be this. And you could even make an agent that makes it so that it uses a translation tool rather than just, hallucinating. Warning: a model's chat template discussed in this section is different from a prompt template used by application developers to hydrate their prompts with specific data. A model's chat template is defined by the model's developers and can usually be found in the model's documentation. A prompt template can be defined by any application developer. Different models use different chat templates. The same model provider can change the template between model versions. For example, for the Llama 3 chat model, Meta changed the template to the following. Ah, yeah, exactly. So this is what I read about recently in my other series on Hugging Face. These are all, there's no standardization of these sorts of special system messages across models, and not even across different versions of models of the same model. Each text span between less than sign pipe and pipe greater than sign, such as less than sign pipe begin underscore of underscore text, pipe greater than sign, and less than sign pipe start header ID, same sort of casing, all lowercase with underscores instead of spaces. Pipe greater than sign is treated as a single token by the model. Accidentally using the wrong template can lead to bewildering performance issues. Small mistakes when using a template, such as an extra new line, can also cause the model to significantly change its behaviors. Tip: here are a few good practices to follow to avoid problems with mismatched templates. When constructing inputs for a foundation model, make sure that your inputs follow the model's chat template exactly. If you use a third-party tool to construct prompts, verify that this tool uses the correct chat template. Template errors are unfortunately very common. These errors are hard to spot because they cause silent failures. The model will do something reasonable even if the template is wrong. Before sending a query, and let's see if my, okay, audio is going. Before sending a query to a model, print out the final prompt to double check if it follows the expected template. Many model providers emphasize that well-crafted system prompts can provide performance. For example, Anthropic documentation says, when assigning Claude a specific role or personality through a system prompt, it can maintain that character more effectively throughout the conversation, exhibiting more natural and creative responses while staying in character. But why would system prompts boost performance compared to user prompts? Under the hood, the system prompt and the user prompt are concatenated into a single final prompt before being fed into the model. From the model's perspective, system prompts and user prompts are processed the same way. Any performance boost that a system prompt can give is likely one or both of the because of one or both of the following factors. The system prompt comes first in the final prompt, and the model might just be better at processing instructions that came first. The model might have been post-trained to pay more attention to the system prompt, as shared in the OpenAI paper, The Instruction Hierarchy, Training LLMs to Prioritize Privileged Instructions. Training a model to prioritize system prompts also helps mitigate prompt attacks, as discussed later in this chapter. Context length and context efficiency. How much information can be included in a prompt depends on the model's context length limit. Models' maximum context length has increased rapidly in recent years. The first three generations of GPTs have 1K, 2K, and 4K context length, respectively. This is barely long enough for a college essay and too short for most legal documents or research papers. Context length expansion soon became a race among model providers and practitioners. Figure 5-2 shows how quickly the context length limit is expanding. Within 5 years, it grew 2,000 times from GPT-2's 1K context length to Gemini 1.5 Pro's 2 million context length. A 100,000 context length can fit a moderate-sized book. As a reference, this book contains approximately 120,000 words or 160,000 tokens. A 2 million context length can fit approximately 2,000 Wikipedia pages and a reasonably complex code base, such as PyTorch. All right, so figure 5-2, the context length was expanded from 1K to 2 million between February 2019 and May 2024. So context length is accelerating logarithmically. Not all parts of a prompt are equal. Research has shown that a model is much better at understanding instructions given at the beginning and the end of a prompt than in the middle. One way to evaluate the effectiveness of different parts of a prompt is to use a test commonly known as the needle in a haystack, NIAH. The idea is to insert a random piece of information, the needle, in different locations in a prompt, the haystack, and ask the model to find it. Um, Figure 5-3 shows an example of a piece of information used in Louis et al.'s paper. So this is figure 5-3, an example of a needle in a haystack prompt used by Louis et al. 2023. So um, extract the value corresponding to the specified key in the JSON object below. So here's the JSON data. This is the value in the middle. There are 5 values. So this is going to be key value number 3 and or key number 3. So and this is an interesting. Okay, so yeah, the key, yeah. So using the term value was enough for it to know to grab this one here and not just restate what the key was there. So good result there. So figure 5-4 shows the result from the paper. All the models tested seem much better at finding the information when it's closer to the beginning and the end of the prompt than the middle. So here's figure 5-4, the effect of changing the position of the inserted information in the prompt on the model's performance. Lower positions are closer to the start of the input context. Okay. The paper used a randomly generated string, but you can use real questions and real answers. For example, if you have the transcript of a long doctor visit, you can ask the model to return information mentioned throughout the meeting, such as the drug the patient is using or the blood type of the patient. Make sure that the information you use to test is private and avoid the possibility of it being included in the model's training data. If that's the case, the model might just rely on its internal knowledge instead of the context to answer the question. Similar tests, such as ruler, can um, also be used to evaluate how good a model is at processing long prompts. If the model's performance grows increasingly worse with a longer context, then perhaps you should find a way to shorten your prompts. System prompt, user prompt examples, and context are the key components of a prompt. Now that we've discussed what a prompt is and why prompting works, let's discuss the best practices for writing effective prompts. All right, so this is kind of like what I would hope that we were reading about initially. Um, I think this is what the people want. They just want to know how to write good prompts. So I think I'm going to end the video here because it's probably been going on for a while, and I don't want this buried at the end of a video. Um, yeah, so well, I've only been going for about a half an hour, but to be honest, I'm kind of rallying through. I just kind of don't have it today, whatever it is. So yeah, I'm going to end it here, and when I come back, we'll this prompt engineering best practices will be at the start of the next video.